The Gate Location Advisor is a great automation tool that lets Moldex3D determine the correct number and location of gates and allows the user to evaluate the implications of different gate placements before even needing to run the analysis. The Gate Location Advisor can be found under the Gate option under the Model tab. So if you click on the drop down here, you'll find the Gate Location Advisor. And there's two uses for the Gate Location Advisor. We have automatic mode and we have manual mode. I'll go through both of these. Automatic mode allows you to have Moldex3D tell you where the gates should be placed on the part. And all you need to determine is the number of gates and any sort of constraints that you want for that gate placement. For example, if I want these gates on a particular surface, we can select a surface and let Moldex3D tell us where along that surface we want to gate. In this case, I'm just going to have one singular gate placement and let Moldex3D tell me where is the ideal place for that gate to be had on my part. To do so, I'm just going to select one number of gates. I'm not going to constrain anything, and I'll hit apply. Once finished, the Gate Location Advisor will give us a singular gate. We can see that this gate is maybe on a weird feature, maybe on a fillet or a side surface or something. The thing to note here is that the Gate Location Advisor will be trying to optimize what's called the flow length ratio. The flow length ratio is the distance from the gate to a particular location of the part divided by the thickness at that location on the part, something that we call the L over T. So for this part with a single gate, we can see that it's biased the gate down towards this side closer to us because of these features over on the right side of the part. And it's also put the gate slightly off center because the flow length to the right side, you can see this feature over here, is longer than the left side. The idea here is to get a gate in a centralized location, and then we can use our intuition to figure out where the actual best gate location would be. So maybe instead of the gate being on the side of this fillet, it could be in the middle of one of these surfaces, or maybe in the middle of this crosshatch feature up here. If I want to constrain my gate into a particular region of the part, I can do that using the constrain gating region. This constrain gating region has two options. You can either constrain a non-gating region, meaning that the Gate Location Advisor will put the gate on any surface besides the one selected. And then we also have gating region, which means that the Gate Location Advisor will be restricted to just gating on the selected surfaces. In this case, let's say I put the gating region on this surface here. I'll hit apply. And we can see that it's placed a new gate up on the top here. But something to keep in mind is that if you have a gate already pre-selected, it will use that in the flow length ratio calculation. So whereas the original Gate Location Advisor placed a gate down here, because I already had this gate and I constrained to using this surface, it put this gate up on the opposite side of the part to try and balance that flow length ratio. Now let's see where it places this gate if I remove the original gate. Going back into the Gate Location Advisor, constrain gating region, and we'll select our gating region as that same surface and hit apply. And we can see that the gate is placed in the middle of this selected surface to optimize the flow length ratio. Similarly, we can select a non-gating region to tell this tool where we don't want to place the gate if there's a Class A surface, and we can constrain this Gate Location Advisor in a similar manner. The other side of the Gate Location Advisor is manual mode. Manual mode allows us to manually select where we want to place the gate and evaluate the flow length ratio as a resultant of that gate placement decision. As an example, I'm going to add a gate, let's say in the middle of this surface. I'll hit manual update and it will readjust the flow length ratio. Ultimately, we're trying to get as low of a flow length ratio maximum as possible. Theoretically, if we have a constant thickness throughout our part, then the length from the gate is what we're adjusting here. If this maximum length increases, then that probably means that one side of the part is imbalanced from the other. Let's see what happens if we put two gates on this feature and remove this gate. You can see I've placed feature lines, so that makes my gate adding a little bit easier. Manual update. And we can see that our flow length ratio maximum has decreased significantly. This should be expected because now we have two gates instead of one gate, so the overall flow length should decrease quite a bit. Now we have to figure out if the weld line in the middle of the part is going to be worth adding a second gate. So let's say I want to gate in this flat center surface on the part, but I don't know exactly where in that center surface I should be gating. What I'll do is I'll select gating mode, automatic. I'll define my number of gates as 1. Non-gating side direction won't matter in this case. When I'm constraining the gating region, it will override this non-gating side direction. I'll check the constrain gating region checkbox, select gating region, select faces. We'll find that middle surface, check mark, and then we'll hit apply. This function is going to find the lowest flow length ratio possible for this surface that we've selected. In most circumstances, we want this maximum flow length ratio to be as low as possible. This is because we're trying to achieve a balanced flow. In this case, we have two end of fill regions. We have one over here on the left side of the part, one over here on the right side of the part. And so I want the melt to arrive at both of those corners simultaneously, or as simultaneously as possible, given the constrained gating surface. In this case, the gate location advisor has selected a gate location such that the maximum flow length ratio is as small as it could possibly be. And you can see that that gating location is actually on the edge of that selected surface. Now, intuitively, we might want to move that gate location inwards, but actually the ideal gate location might be on one of these side surfaces or one of these smaller surfaces in the middle. Could be something to investigate, but I'm going to assume that we just want a gate on this flat surface. Now let's see what happens if I move this gate inwards a little bit. To do so, I'm going to switch over to manual mode. All right, in manual mode, I can either add, move, or remove a gate that already exists. In this case, I'm going to move the gate that already is here. I'll select my gate to move, press the check mark. Reference point will be the end of my gate. And the destination point, sometimes you'll have to turn off the ortho snap to find this. Maybe I'll just move it inwards a little bit on the surface. Now, what I'm going to pay attention to here is the maximum flow length ratio. If that decreases, then that's great. If that increases, then that's a negative change. I'm going to hit manual update over here on the left side, and we can see that our maximum flow length ratio has increased from that 86 number to about 90. This means that we're trending in the wrong direction as far as a balanced flow is concerned, and maybe the left side of the part and the right side of the part are becoming less balanced with one another. Being that we're moving the gate further away from this feature over here, it tells me that this corner is probably the highest flow length ratio. Let's see what happens if I move the gate a little bit closer to that feature. All right, we see that we get closer to what we started with, around that 86 number. And so it seems like moving diagonally is a better move than moving straight inwards on this surface. Once I have a nice balanced gate location, as low of a flow length ratio as I possibly can get on the constrained surface, I'm going to hit show L over T band. And this will allow me to visualize the relative melt from progression based purely on this flow length ratio plot. This black band represents a particular value on this flow length ratio scale. All right, as I move the slider towards the right, you can see that the melt converges on those end of fill regions over here and over here. And we can see that they converge pretty much at about the same time. This would indicate a balanced flow, and I could proceed from here to run a filling analysis. Let's see what an imbalanced flow looks like. To visualize this, I'm simply just going to move the gate from where it was to maybe over here on the surface, manual update. And so we can see with this L over T band, This side converges much earlier than this side, indicating an imbalanced flow. Going back to the previous gate location, one last thing that we can visualize is what material we could possibly use to make this part. Right below the show L over T band slider is the typical material L over T value table. And so we're looking for this maximum flow length ratio to fall within the range specified. More specifically, we're trying to get the maximum flow length ratio below the maximum value of this range. If you're over the maximum value of the range, it means that we're trying to push the material along too far of a flow length. And so in that case, maybe we will need to add additional gates or select a lower viscosity material. You'll see in the case of PC, the range is quite a bit smaller in magnitude than a lot of other materials. This is because PC is much more prone to shear than something like a polypropylene, which is somewhere up in the 230 to 340 range. Now, if we're above the maximum value that indicates that we're trying to push the material too far, if we're below the minimum, that's actually not too big of an issue. It just means that we could possibly use a higher viscosity material. In this case, if we're trying to use polypropylene, we are very far underneath the minimum, and so we could consider using something much higher in viscosity, something similar to that. Something to look forward to in the future is, in addition to the L over T through the Gate Location Advisor, we're going to be implementing a feature into the ISLM platform, which will allow us to look up historical data. In the case of this dashboard, maybe we look at the number of gates as well as the relative location of those gates to determine for a new design how many gates and where those gates should be placed. The way this function will work is you're just going to import your part geometry, and the ISLM platform will look for all of the projects that you've run in the past. And based on a similarity index for the part volume, thickness distribution, gate count, sprue pressure, etc., it will suggest a number of gates and the location of those gates for the new part design. Thanks for watching this Moldex3D Gate Location Advisor tutorial, and we'll see you in the next one.